In everyday life, individuals often face limitations set by their life partners. In this context, classical mechanics offers several insights into these constraints. Now we may pose a question: what are constraints? The geometrical restrictions imposed on the motion of a system are termed as constraints. For example, consider the behavior of gaseous molecules within a container. The walls of the container provide limitations for these molecules, which is the sole reason they are able to move inside without any possibility of escaping. In the absence of the walls of the container, the gaseous molecules should come out of this system. Here, the constraints are nothing but the walls of the container. Now we may classify the constraints majorly into two categories. One is holonomic and the other is non-holonomic. In holonomic constraints, the constraints are expressed as equations that relate the coordinates and time having the form f of r1, r2, r3, r4, r5 up to rn, t equal to 0. In a rigid body, the distance between any two particles of the body remains constant during motion. This is an example for holonomic constraint. To understand more about this, examine the movement of a dumbbell situated in the xy plane. The masses m1 and m2 are connected by a rod of length L. Despite the motion of the dumbbell, the length of the rod remains constant. Mathematically, we can write x2 square minus x1 square plus y2 square minus y1 square is equal to L square. If you bring this L square to the left hand side, the right hand side is 0. If you write an equation of constraint in this form, which represents our holonomic constraint. So this is the general equation representing the motion of the rigid body. Here c is a constant. If you shift this c square to the left hand side, the right hand side is 0. Now we have to talk about non-holonomic constraints. The constraints expressed by an equation in the form of inequality are expressed as non-holonomic. The equation of constraint in the case of a particle moving on or outside the surface of a sphere of radius R is an example of non-holonomic constraint. See this diagram. Here the particle is moving outside the sphere of radius r. Therefore, x square plus y square plus z square is greater than r square. Suppose the particle is moving on the surface of the sphere of radius r, we should write the equation x square plus y square plus z square equal to r square. By combining these two, we have presented the equation in this form: x square plus y square plus z square greater than or equal to r square. If the particle is moving on the surface, the equality sign holds good. If the particle is moving outside the surface, the inequality sign, that means greater than, should be taken in our account. We know that the position vector r equal to I into x plus j into y plus k into z. Then r dot r is our r square. The value of r square is x square plus y square plus z square. Now this equation is modified in this form. If you bring this capital R square to the left hand side, right hand side is 0. But anyway, here we are using inequality sign. That means greater than or equal to. Therefore, this represents the non-holonomic constraint. With the help of these two things, we may introduce the concept degrees of freedom. The number of independent ways in which a system can move without violating the constraints is called the degrees of freedom. Examine the dynamics of a system comprising n particles within a three-dimensional space. In the absence of any constraints, the system possesses 3n degrees of freedom. Suppose if a system contains 3 particles, in the absence of constraints, the degrees of freedom is 9. If you add the constraint in our account, the degrees of freedom f is equal to 3n minus k. Suppose the constraint k is 2, then the degrees of freedom for a 3 particle system is f is equal to 9 minus 2, that is 7.